So thank you again for joining. I wanted to go back to this point very briefly. So Norbert Wiener in 48, the same who wrote the paper on the Tauberian theorem, that is one of the foundational results in this nonlinear approximation theory that then led to all these results on interpolation by neural networks and expressivity of these constructions that, as you have seen yesterday, are very much based on these ideas of time discrete dynamical systems, layer by layer, like in Markov chains, but involving in a critical manner the nonlinearity that allows you to focus on specific pieces of information and orient the information to, say, left and right, something that is extremely important for the expressivity. The same who did that later got interested in control theory. He rescued the term cybernetics that was coined initially by Ampère, the French physicist Ampère, and he redefined it as the science of control and communication in animals and machines that, as we said, is very much anticipating artificial intelligence. So somehow what we see today in machine learning is very much the output of, the integration of all these concepts and technologies that were developed, in particular in the context of control optimization. You have seen also in this video and in the previous lectures that, training the parameters is the key word. So even once you adopt a given architecture and you define the sigmoid activation function, say, for instance, ReLU, once you fix the architecture and the ReLU, you still need to find these parameters. And as we were explaining, these parameters are computed by minimizing, by solving an optimal control or optimization problem. So you see that training is very much like optimization related to PDEs, ODEs, or in this case, its discrete counterparts, okay? So all these things are very much related. Machine learning and artificial intelligence has been very successful on putting together all these ideas. Of course, for the optimization, you have to use all the tools in optimization and control. So gradient, of course, you will use the fundamental ideas of the calculus of variation, like the direct method of the calculus of variation to guarantee that a continuous, convex and coercive function has a minimizer in a Hilbert space. If it is not convex, but it is compact, the minimizer exists too. Then you have gradient descent, which of course is very nice for convex functions, but only guarantees local success to the local minimizers for non-convex functions. For computing the gradients, and this is also an idea coming from control theory, probably very much due to Pontryagin, there is the use of the adjoint in order to more easily and cheaply and faster compute the gradients. There is also the concept of stochastic gradient descent, which is basically aimed to tackle two different issues. One is the lack of convexity. So you know that when you are dealing with a functional that is non-convex, if you apply gradient descent, you will be trapped in the local minimizer. So you need some stochasticity to quit possibly local minimizers wells that are very far from the global minimizer. So it's good to let yourself from time to time to change the position of your iteration in your gradient descent and to visit other scenarios where, the functional can be even lower. So stochasticity helps to this, escape from local wells, and also very much like, for instance, in random batch methods, the stochastic gradient descent is very often used in order to avoid the computation of the full gradient. Recall that ChatGPT 3 was using 175 billion parameters, 175 10 to the power 9, which is 20 times the population of humans on Earth. So if you try to apply the gradient descent algorithm, well, theoretically it's very simple. The gradient, you say, what is the gradient? Oh, the gradient is a vector. And what are the components of the vectors? Just the partial derivatives. Yes, but how many partial derivatives there are? There are 175 billion parameters, therefore also partial derivatives. You don't want to compute all of them. So it's much more natural to apply an alternating method in which in every step you employ one derivative, directional derivative, or a block of derivatives, so a batch, right? But because you don't know exactly in which order this has to be done, it is natural to randomize this procedure, and this is the so-called random batch method, which guarantees that indeed in high probability you will keep getting closer to the minimizer, but by making the computational burden much lighter. So keep in mind that in these huge neural networks, just the effort of running an optimization loop to train the parameters can cost millions of euros and will need, hours of, the best high performance computer you can think of. And this is why these efforts nowadays are very often being led by private companies and not universities or research centers, right? So conceptually, it's very much like classical discrete optimization using gradient-like methodologies, but the size and the complexity of the problem makes it so giant that you really need a lot of resources, okay? So for instance, recently we had a meeting in Fudan in Shanghai. One of our colleagues, Xiaoming Yuan from Hong Kong University, was there. He's collaborating with Huawei in Hong Kong. For instance, he told us that the computers they are using are located somewhere in Mongolia, where, for instance, the cost of energy is less. So even the energy you need to burn in order to run these training processes is so high that you pay attention to where you are going to locate your computers, right? So very much like the debate these days in Spain about whether Repsol will do the next investments either in Spain or in Portugal next door, depending on the taxes they impose on the company for these new endeavors. Very good. Okay, so now let's see more precisely. This was Kalman, 58, 10 years after Norbert Wiener. So you see things are getting accelerated, but still progress is slow. It took 10 years from the very definition of Norbert Wiener about what cybernetics was, 48, to Kalman, 58, to state a very clear result on the controllability of finite dimensional linear system. So you see x prime equal ax plus bu. This is a linear finite dimensional control system in which the state x belongs to the Euclidean space of dimension d. Traditionally, you will be thinking on, for instance, how to control the position of a rocket or a car, but in the context of machine learning and data science, x can be an image. As we said yesterday, 28 times 28, I think it was like 784 dimensions, okay? So it could be, that x is representing images in the folder of your computer that are living in a Euclidean space of dimension 784, right? And are evolving there to go to the correct folder according to the, the classification you aim in your folder according to your family members, colleagues, and friends. Okay? Now, the dynamics of the system here is given in the traditional paradigm of control. You know the dynamics is given by A. A is very much like a connectivity matrix on a graph, right? So the different components of the vector are interacting. This matrix normally is coming from mechanics. So we use classical Newtonian modeling from mechanics to determine what the A is. We also have a control mechanism that is represented by the matrix B. So we know how the different actuators we can maneuver on the system are influencing the different components of the system, not all equally. It's like when you, I don't know, in your laboratory open a window in an office, you know that, of course, the cool air will enter the first office very rapidly and this will diffuse, but clearly the action of opening the window has an immediate impact on that room and a milder impact on the other. So this is represented by the vector B or matrix B that is somehow saying how much the action of the control U is influencing the different components of the system. So in general, you can have one control or several controls. So we say that we have M controls. Of course, in practical applications, we have much less controls M than components on the system. This is the case when we drive a car. A car is a very complicated engine, and basically we are maneuvering the car by simply using acceleration or brake, one control, acceleration and brake, and the other one is gear, orientation. So two controls for a very complex dynamical system, okay? So typically D will be larger than M, and of course the dream will be to control the system by just one single control scalar UT for M equal 1. So can just with one magic finger control the complexity of the whole dynamics. This is like, for instance, thinking on neural networks, on social networks. D could be the number of individuals in a group, and if M is equal to 1, this will be the role of the coordinator or the influencer of the network that somehow everyone follows, creating opinion just by his or her input, okay? And then Kalman was clear. He said, listen, a problem that makes very much sense is that on controllability. Controllability means that I give you a time window, 0 capital T. I mean, you have 1 day to deliver your work. There is a time horizon, finite, 0 capital T. You know that you are standing in the initial position x0, and you want to bring the system to a different position x1, right? So you give me x0, origin, you give me destination. Can I find the control UT so that the solution of this system will bring x0 to x1? Of course, you could decide to do nothing. I say, no, I will not use controls. I like to I don't like to interfere with the spontaneous dynamics. Well, if you don't do that, if you take U equal to 0, you know what the solution of the system will be x of t exponential at applied to x0. So if you do nothing, this is what you get. But if you control, then you apply the variation of constant formula, right? And this is what allows you to govern the dynamics of the system. So Kalman said, a system is said to be controllable if and only if for every x0 you give me, for every x1 you give me, origin and destination, and for every time window you give me, I can find a control UT so that the solution at t equals 0 takes the value x0, and at t equal 1 takes the value x1. And he checked this. He used the polynomial expansion of the exponential of A. When you are dealing with matrices, you know that the exponential of A can be written as a power series expansion. He used Cayley-Hamilton theorem that says that every matrix is a 0 of the corresponding characteristic polynomial, and he found this algebraic condition to say, listen, a system is controllable if and only if, when you compute the rank of this matrix, B, AB, up to AD minus 1B, you have filled the whole space, the rank of this matrix is full if is D. If for any reason you compute this rank and you get less than D, the system is not controllable. For instance, if you get D minus 1, it means that one of the components of the system is not controllable. So this is why, for instance, if you give me a car and you ask me, is the car controllable in the three-dimensional space? I will tell you no, because I don't have vertical propulsion. I will need an helicopter to be able to control the engine in 3D. The car is controllable in 2D, so D equal 2, but not in 3D. So even if I embed the dynamics of the car in the three-dimensional space, if I do that, D will be 3, and when I compute the rank will be 2. Okay? So this is a fantastic answer then there are in the controllability, there are plenty of literature. There was, for instance, this seminal paper by David Russell published in 1978 in Science Review, in which he was trying to go presenting what was done until then in order to extend the final dimensional control theory into the PDE setting, wave equations, systems of hyperbolic equations, heat equation, and so on. Then in 1988, there was the seminal paper by Jacques Lyons, also in Science Review. 10 years later, where, the scope of applications to PDEs was, enlarged significantly. And many of us have been working on this topic for now 36 years. And the theory has grown a lot. This was one direction of motion. Understand that Kalman was clarifying this topic for finite dimensional systems, and then inspiring continuum mechanics move into the direction of PDEs. Okay. Of course, at that time, because we are more, say, theoretical analysts rather than computational scientists, we didn't really think on the complexity that this result is manifesting. So you see, Kalman says something very simple. If you want to check whether a system is controllable or not, you have to compute this rank and then check whether the rank is D. Okay? But think that you are, for instance, dealing with images in the context of, image classification, as discussed yesterday. Then the dimension is 784. So this means that this matrix A will be a square matrix of size 784 square. And then the corresponding control matrix, even if there were only one control, it will be a column vector with 784 components. And here, because D is 784, here you have 783 powers of the matrix A. I mean, you don't feel like doing this by hand. This is not an exercise you want to do by hand. Of course, when you open the MATLAB toolbox in control theory, you will see that there is one of the commands is to compute the Kalman rank, because it's so fundamental in control. This is the first test. You give me this linear system, the first thing I have to do is to compute the Kalman rank to see whether the actuator B is smart enough to be able to control the whole system or not. So Kalman rank is the first thing you have to do. Therefore, there is a command in MATLAB to do it. Now, I really don't know. Maybe you know better than I. If someone knows, please put it on the chat. I don't know, what is the size of the matrices you can handle with the standard MATLAB in your personal computer. But certainly there is a limit. And this is where this new breakthrough came, right? Where people, the company DeepMind, developed new tools to multiply matrices, very much is inspired in alpha tensors and the ideas of machine learning. So you see that initially, we started by thinking on how to control the classical systems in engineering, like the governor engine, in order to keep, pressure on the locomotive constant to guarantee, performance of our transportation systems. Then mathematicians developed the corresponding theory, Norbert Wiener, Rudolf Kalman. And then for many years, we were working on the extensions of this theory to nonlinear control problems or to PDE problems or to the stochastic PDE problems. But people didn't really think on, well, and how do I actually check this kind of very fundamental conditions, hypotheses to check controllability? And now we see that artificial intelligence is helping us to do it. So you see that we are in a constant loop. You open the book of artificial intelligence and you see plenty of ideas and methods that are coming from control and optimization. And you say, oh, then artificial intelligence is a descendant of control and optimization theory. Yes, but when you see now the state of the art of control theory, when aiming to be applied to very challenging and contemporary applications, which are of very high dimension, you see that we need also the aid of machine learning. So this is really, enriching. The two fields are mutually enriching. We have seen yesterday that an optimal control strategy is not so easy to find, is not so easy to get. So this is computed, of course, using the Pontryagin maximum principle. This is the optimal parking strategy. Many of us will not be able to mimic this parking strategy and probably will need several iterations to implement it. And as I mentioned here, the first paper on control very often that people recognize as the starting point of the analytical mathematical theory of control is this paper by Lord Maxwell on governors, where it was very much about, how the dynamics of a damp harmonic oscillator behaves. And the key observation was that if you put here the amount of damping and here the energy decay, the path that determines how fast the energy decays depending on the size of the damping, in a rather anti-intuitive manner, this damping rate is not monotonic, but actually there is a threshold after which you experience the phenomenon of overdamping. Overdamping is like an overdose, with that you can experience even with coffee, right? One coffee is good. Mathematicians, we transform machines into coffee into theorems, as Paul Erdos said. So yeah, we want to be good mathematicians. So you drink one coffee and you feel better, and two and three and n. But after some n, everyone has a threshold. After drinking too much coffee, you will feel bad. This is the typical overdose phenomena. And what Maxwell indicated is that control problems also very often experience this. So you cannot do better than a given threshold, right? So, and this is particularly evident in the case of parking this car, in which, well, you could try to do better, but you will not do better than this. This is the optimal control strategy, given the constraints you have, at least if you don't want to collide with the cars that are in front and on the back, something that, by the way, many of us do to trick, the problem. Okay, so there are many applications of classical control theory. In the video I have shown you the first day, you see this application of herding, combining model predictive control and random batch method. But our goal was to get back to machine learning and better understand what is the way machine learning benefits from these control ideas. So one of them, there are two different problems. One of them is training effectively these neural networks is a deep, complex, discrete optimization problem, and you have to use all you know about computational optimization to do it successfully, and you need big machines, right? And this is why, as I said the other day, the trend nowadays, very much when building machine learning codes and architectures, is very much like you adopt a large language model and you do the fine-tuning, hoping that in this way the initialization that has been done in order to build this large language model benefits you in the sense that the amount of post-training you have to do, the fine-tuning you have to do is not that heavy, okay? Instead of building your neural network model from scratch, you start from the top, you take this large language model in which plenty of work has been done already, and now you fine-tune it, you project it into your application, okay? So one thing is where one aspect in which control optimization enters the training, the effective computational training of these architectures. The point I'm making here is a bit different. What I'm trying to show you now is from a dynamical perspective, as I was explaining yesterday, how a deep neural network is just the classical PDE in which X is horizontal and time is vertical. A deep neural network will just rotate axes so that X now, the different neurons in every layer are representing the nodes of a space-like discretization, and then time evolves in a discrete manner layer by layer. How the control ideas for ODEs and PDEs allow us to explain the success of machine learning. Okay, so let me show you now an exercise, very simple, that very much fits in this ambition of Norbert Wiener of interaction of machines and animals. And also this very original pioneering aim of that already Aristoteles advocated for. Humans should build machines to do their own task so that they are free to do what they really like to do. So now I can concentrate on talking to you because all the rest is automatic, heating in my office, internet in my office, light in my office, everything is guaranteed automatically. The computer is working autonomously. Everything is operating independently in an automatic manner, so I can concentrate on talking. Okay, it will be much harder if every minute I will have to, regulate the heating, regulate the light, make sure the internet connection is on, and so on. Okay, so how can we employ the very ideas of control theory, in particular, this idea of, Kalman, that information is being propagated, and you can see through this algorithm of computation of the rank. Step by step, you enrich the space you can visit until you are in conditions to guarantee that from the initial configuration you can get anywhere. How layer by layer we can exploit this Kalman understanding to also explain the success of machine learning. This is a very simple supervised learning exercise. We humans know how to do it. We have to classify trash. There are 4 baskets, yellow for plastic, green for glass, blue for paper, gray for organic. So if you give me, I go to my kitchen and I have to organize things, I don't have any difficulty. I can distinguish plastic from paper, I can distinguish glass from organic, and then I can put everything in the corresponding trash. Okay, but this is not a job you would like to do. So I would like to build a robot that is able to do this. Okay, so what is a robot? Well, a robot is an engine. This engine is driven by some computer code, and this computer code, after all, is just the computer representation of a function. So we need a function that is putting each item in the corresponding basket. How do we do that? We take pictures of each item, then each item, by taking just a photo with our cell phone, becomes a point in a Euclidean space of dimension 784, so the dimension is 784. And then, for instance, for arrival, I can just take R2, so M, the space of arrival, can be 2-dimensional, and I say that the corresponding baskets are simply collocated according to the axis, for instance, like this, right? The different baskets, well, here should be gray. I don't see the gray. Okay, I do it black. Okay. And then what I try to build is a function that will take each of these. You see that this object here is a point in the Euclidean space of dimension d equal 784. And I want this function f to bring this point to the yellow one. And I want this function f to take this point, which is a different point in the space of dimension 784. I want it to go to the green basket. And I want, cheese, which is organic, which is a different point in the space of dimension 784 to go to the gray basket. So I need a function that is mapping each of these objects, points in the Euclidean space of high dimension d 784, to the corresponding baskets, which are represented by, for instance, points or a small disk in this two-dimensional Euclidean space. Can I do that? And yes, the answer is yes, you can do that. There are many ways you can build a function, right? Building a function from Rd into R2 that is able to take specific values on this. How many? 1, 2, 3, 6, 8. 8 times 4. So I have 32 points, different points in the Euclidean space in which I have to take different values. There are many ways of building this function. Okay? What we want to do is to do it using neural networks and explain why control theory can help you on doing this. Okay? And now recall what the goal is. The goal is not to build a robot that could organize my kitchen, putting these 32 things in the corresponding baskets. This is something I can do. I mean, I can do it even during the coffee break we will take in half an hour. I can just devote 2 minutes to do this myself. No, what I want is a robot that will learn from this exercise so that in the future, the robot can do it himself without my intervention. So what we want, I don't want this function just to make sure that each item goes to the corresponding basket. I can do that myself. What I want is a function that, because it's doing this well, whenever there is some new item coming, right? I'm cooking and there is a piece of carrot, it's a leftover of a carrot, the robot knows, oh, carrot is organic, goes to gray. So we want a function that will generalize properly. And as we have said, this is precisely the challenge. We have seen yesterday, for instance, that ChatGPT, being extraordinary, doesn't generalize well when building a mathematical bibliography because it can create fake references. Okay, so fake references will be take the piece of carrot and put it in the green. It's a failure. Okay, so but we know that in this context we never expect 100% accuracy. Actually, there will be even some cases where and there are cases where you take a bottle and you wonder yourself, so is this plastic or is this paper? Not clear. Sometimes nowadays there are these composite materials for which it's very hard to say. So even ourselves that claim to know how to do this classification, we do mistakes. So of course, we don't expect 100% generalization capacity, but we expect to maximize it. That is our goal. Okay? And as I said, this works. You take this neural differential equation, right? This is a 2D plot of a 3D simulation. The exercise is clear. There were purple tennis balls, yellow tennis balls, and green tennis balls. Each of them had to go to a basket, and we have built a robot. The robot is this neural differential equation that takes each of these items, right? And along time, in the time interval 0t, brings them to the corresponding basket. How did we do it? We employed ideas from control theory. and computed the controls W depending on time, A depending on time, and B depending on time. Let me remind you that this was a d-dimensional vector field. This was a scalar, and this was also a vector field of dimension d, so that, at every time, you are determining what is the velocity of each tennis ball that has to get into the corresponding basket according to the color. The main difference, as I said yesterday, with respect to Kalman, there are two differences. One is this model is nonlinear. It doesn't really fit in the Kalman paradigm. In the Kalman paradigm, A is a linear model. So here, sigma is nonlinear, but this is very important. This is something we have learned in machine learning. Sigma is very much needed in order to classify, because it's the only function that can push part of the items to the left and the others to the right. So sigma is very much needed, it's nonlinear. And second, contrarily to the problem that Kalman solved, here we are not dealing with bringing one initial datum to the corresponding target, but we want all the initial data to get to the target simultaneously. So it's a simultaneous or ensemble control problem. Okay? And then you can find the answer in our paper with Dominic Ruiz-Vallet in 2023, published in Science Review. The answer says, yes, you can. In dimension 2 and higher, not in dimension 1, because on the real line, particles will collide if you try to place them differently as they are initially ordered. You need room. You need dimension 2 or higher. Give me n data. Give me m, say, locations, m baskets. I can always find a control which is piecewise constant, so it's of bounded variation in any time interval that is able to bring all the data to the corresponding destination. And the proof is very much inspired on how the Rubik Cube operates. We all visualize how the Rubik Cube is solved. We need to iterate. You see that you cannot do it in one shot. You need to iterate. And in every iteration, with one hand, you keep part of the cube fixed, frozen, while the other one is rotating. So we iterate motions in which you very much see what the ReLU does. Part of the cube is frozen, the other one moves. Now, let's see how and why this neural differential equation is able to mimic the behavior of the Rubik cube. Okay? Let me recall you the dimensions and the notation. So even those that got lost until now, please focus now and you will understand 99.9% of everything I'm saying. Okay? So X lives in RD. Trial X lives in RD. Okay? It can be any dimension. It can be a low-dimensional system. So, for instance, assume you are classifying blood tests in the hospital, and you are in charge of that. I mean, you can do it one by one. But a blood test in the hospital, I don't know how many parameters appear on a standard blood test. How many? 40 maybe? So 40 numbers. So you are dealing with a vector of dimension 40. You are dealing with low-resolution images. This is going to be 784. If you are dealing with a magnetoresonance out of an MRI, I really don't know what is the volume of this image, but it's huge. The dimension is huge, right? Where you see all the details of, the inner human, skeleton or organs. So huge dimension. Doesn't matter. For us, the dimension is anything greater or equal than 2. Okay? Now, sigma is the ReLU. Sigma is the ReLU. So sigma is the ReLU, we know. ReLU. This is a scalar product. X lives in the d-dimensional space. The dot here is just time derivative. So this means that at every time, x dot is giving me the instantaneous velocity of each of the particles. It could be these blood tests, these magnetoresonances, or these images that I'm trying to put order on in my photo folder in the computer. B is just a drift, a scalar function. At any time, this belongs to R. This is a scalar product, so A is a vector in RD. And of course, the output of sigma, so you see sigma is applied to this, which is a scalar number. Sigma applied to this scalar number is a scalar. And I vectorize it by taking here a column vector RD. So in this case, the number of controls is 2D plus 1 at every time instance. In practice, of course, we will discretize this ODE on time to reproduce the same pattern in a time-discrete manner, layer by layer on this residual neural network. Recall that this neural ODE, by Euler discretization, becomes a classical residual neural network. Depending how many steps you do on time, the deeper this neuron will be. But think that we are, the way we draw this is a column vector for the position, initial position of X that is evolving layer by layer. Okay? Very good. Now, let's think a little bit. What is the behavior of a given particle xt at time t according to this ODE? Well, the only thing I have to do to determine what the behavior is, I have to check in which direction it's moving. So I take this particle xt, positioned at the point xt in the Euclidean space RD. I look the velocity, x prime, and I know this particle is moving in this direction. So the purple tennis ball is going in this direction, the yellow tennis ball is going in this direction, the green tennis ball is going in this direction. What is the direction? Is given by this. And when I check this, the first thing I observe, what is relevant here is whether A dot x plus B is negative or positive. Because if A dot x plus B is negative, then sigma is 0, and this means that this tennis ball is frozen. So you see, the neural differential equations are artificial dynamical systems, are synthetic dynamical systems. This doesn't happen in nature. If you put n tennis ball in motions, they will all move according to gravity. So in this synthetic model, you have the possibility to freeze the evolution of some of the tennis balls while the others are evolving. So if A dot x plus B is 0 or negative, sigma is 0, and the corresponding tennis ball doesn't move. And whenever A dot x plus B is positive, then sigma is the identity. And if this is the identity, then the right-hand side in this product is W times A times X plus W times B. So this is a non-homogeneous linear differential equation whose solution is just given by an exponential. So half of the space is frozen, the other one evolves, and it evolves very much in the direction given by the W. So what we are doing in this neural ODE is at every time instance, I'm using my two hands. With one hand, I'm cutting a space into two halves, like here. This is the hyperplane. By choosing A and B, I determine the cutting hyperplane. And I also determine what is the frozen part. So here, frozen is at the upside, 0. And what is the active part? And with the left hand, I am choosing the orientation of W that is put in the wind that will push in any of the possible directions of the Euclidean space. So one hand is one control, A dot x plus B, A and B, that determine the cutting hyperplane. And with the other one, I move the active part of the half space. So very much like in the Rubik cube, one hand just to hold part of the cube frozen, which is like defining the dividing hyperplane, and the other hand just to rotate the active part in the corresponding direction. And now, if I use this idea, and very much like in the Rubik cube, and I learn how to do it once, then by induction, I can prove the theorem in any dimension. So you see, Now, the second link between control and machine learning is to say, listen, not only you have to use the classical tools of optimization theory and control to train a neural network. That's certainly something you have to do. All optimization theory has to be used in a very smart manner in order to train a neural network. But in fact, the second and very important use of control in machine learning is to explain why these constructions, like the residual neural networks, for instance, are able to learn. They are able to learn because they do behave as we want, solving this simultaneous or ensemble control problem. If you are able to solve this ensemble or simultaneous control problem, is because this is what explains that your neural network has learned. Your neural network has the capacity to represent. The neural network has the capacity of classifying properly data according to their labels. Okay? So that's the link I wanted to tell you about, and this is the logo of our new ERC funded project, very much devoted to develop these ideas in the interface between control and machine learning. So I like this logo very much. As you see, somehow is denoting dynamism, complex behavior, and also these neural ideas. Okay, so I don't want to spend time on this. In our webpage of our group, you can find plenty of information about what we are doing. We have also positions available for young people, PhD students, postdocs, senior visitors. So let us know if you are interested on collaborating with us. I will be very happy. Okay, so to move on, the other day I was mentioning this topic of PDE plus D. So how we integrate data more in our, all life of PDE modeling, analysis, dynamics, numerical simulation, and so on. So this is a joint work with Lorenzo Liverani and Siki and Lee, actually also with Kang Liu, who is now maître de conférence in Dijon, in France. He was former student of Frédéric Bonans. He was with us for a few months as a postdoc, and now he's a permanent maître de conférence in Dijon. So the first problem we thought of was the following. Listen, we have seen that a neural differential equation is able to bring initial data from the initial configuration into the final configuration, very much like classifying tennis balls into different, say, baskets according to colors, okay? Now, how can I use this idea if I want to move further and try to build a synthetic model? Where I say synthetic is artificial, and I insist, right? So I insist that, this neural ODE very much represents the fact that we are in the world of synthetic models, because I'm not building these ODEs based on the principle of mechanics. I am just building the ODE in a totally arbitrary manner. I could even choose the sigmoid differently, not necessarily the ReLU, and the theorem will be the same. Our theorem is not only valid for the ReLU, you can take other activation functions and you will be able to prove it as well, okay? So it's purely artificial, it's purely synthetic. There is nothing inspired on, real mechanics here. We just adopt this model in a totally artificial manner, and we build the synthetic model by just tuning the control parameters. So how can we push this synthetic modeling perspective when the problem now becomes a bit more complex and is of the following nature. Now you see here you have 1, 2, 3, 4, 5, 6, 7 dots, I think, right? So you see 7 black dots, 7 blue dots, 7 red dots, 7 green dots, 7 yellow dots. What are these? Sensors located in different places. For instance, you are tracking pollution in Guadalquivir, the Sevilla river. When passing by Sevilla, you are trying to track pollution in your river. So you have 7 sensors located in different positions. And every 10 minutes, each of the sensor is giving you the value. Okay? So in this way, you can monitor whether the river is clean, and so that people can swim or can use the water, or whether there is some alert and you have to take some, adopt some restrictions. You all recall the debate in the Olympics whether the Sena River was good or bad for swimming competitions and so on. Okay? So here is the same. So you have 7 sensors every few seconds or minutes from time to time in a regular manner, probably. This is programmed. They are giving you measurements. So the first measurement at t equals 0 is the black values. So in this case, because the representation is in 2D, I am assuming that at every time instance, the sensor is giving me 2 informations, 2 parameters, 2 values. So I place them on the plane. So the black dots here is the value that the 7 sensors give me at t equals 0. Different locations, different values, different dots on the plane. After 10 minutes, the sensors give me these 7 values. After that, they give me the green values. After that, they give me the yellow values. After that, they give me the red values. After that, they give me the purple values. Okay, very good. And then I say, well, this is what I see from physics. So I have sensors. There is a physical process ongoing. And these are the measurements I am getting. Question: can I build a dynamical system that is able to track all this data so that at t equals 0, these 7 trajectories are located at the black points, 10 minutes later they are in the blue points, and so on? Can I do that? Well, maybe I will say, well, this is water, pollution. There is a book on pollution on rivers. Let me open the book. Let me see what are the models, or maybe shallow waters with some, components about, particle motion. You will get a couplet system, particles, fluid mechanics, ODs coupled with transport equation, maybe shallow water equations. It will be very complicated to do it using mechanics. This is certainly something you can do, but it will take a long while. But then we have learned that a cheap way of modeling data using dynamical systems and control ideas is just use synthetic models. Can I build a synthetic model that will be able to capture all the informations that these sensors are giving me? And the answer is yes, I can. And this is the output. Okay, so it works. I have here now a synthetic model that is able to do this. And as you can guess, the only thing I have done is to reiterate the result I have mentioned before from Sarayan review again and again and again by simply tuning the parameters of this neural ODE. I just tune them so that from t equals 0 to t equal from T0 to T1, I move from the black configuration to the blue. From T1 to T2, I move from the blue configuration to the green, and so on. So I just reiterate again, right, a long time, this interpolation process, and I can build an artificial neural differential equation with piecewise constant coefficients W, A, and B that will be successfully able to track this data. Okay? Now, what is the value of this? I don't know. But the answer is yes, we can. And you don't need to know everything in continuum mechanics and the modeling of particles evolving in fluids and so on in order to do that. You can just do it using synthetic neural network models. This simple exercise and this video that I find personally beautiful, I think expresses well to which extent these new tools in machine learning can be an aid, at least, I don't say a replacement, but of some help when tackling complex applications in which maybe you don't have a priori a very good modeling paradigm. If you don't know about the modeling paradigm, just use synthetic models and you will always be able to track data. So this is dynamical system learning out of time-like data, something that happens very much in applications. If you want to understand how population or how traffic is ongoing in your town, maybe it's not so easy to write a PDE, but you can simply observe the motion of the cars by the GPS of the cell phones of the drivers, and then you can interpolate and get a huge artificial neural network system that will be able to interpolate the data. Okay? So we didn't have time to look more videos of 3 blue, 1 brown. I really recommend you to have a look. Maybe I can tell you briefly about them. So this is the first one we watched yesterday. Then the second one is precisely on what we were discussing today, that if you want to do the training, you have to solve an optimization problem. You have to define a loss functional based on the data you have, in the case of supervised learning. And then you have to apply gradient descent like ideas. Okay, so this is the second video. The third video gets a bit more into the details of how this gradient descent goes and how things work. And actually the key is in the chapter 4, which is about backpropagation. And, for people in control theory, this is something we know well. This is the adjoint methodology. And recall that in control theory, we have a dynamical system that is evolving forward, while the adjoint is coming back, is evolving backwards. And this is what in machine learning is called backpropagation. There are actually, 4 videos about backpropagation. This is just the adjoint methodology in calculus with a different terminology. The big difference being, of course, as we said, one is that the system we are considering here, this is time discrete, evolving layer by layer. So it's time discrete, not time continuous, as when we are dealing with ODE or PDE control. It's time discrete. The second one is that the depth is not increasing as delta t goes to 0 as in classical ODE or PDE approximation methodologies. So the number of layers is fixed by the architecture you have chosen, can be large or small, but is the same discrete dynamics. The dynamics is evolving horizontally. This is time, and this is space, say. And the other aspect to take into account, of course, is that because the original system is nonlinear, sigma, the adjoint, you have to linearize the system to compute the adjoint. But this is also classical for nonlinear ODE and PDE control problems. The next one is the large language models. So maybe we have a look to this. I think this is important.
The initials GPT stand for Generative Pre-trained.
Can you hear and see the video?
Yes.
Okay, so this is large language models,
The first
ChatGPT.
word is straightforward enough. These are bots that generate new text. Pre-trained refers to how the model went through a process of learning from a massive amount of data, and the pre
We can't hear anymore, I guess.
We can't hear now.
underlying the current boom in AI. What I want to do with this video and the following chapters is go through a visually driven explanation for what actually happens inside a transformer. We're going to follow the data that flows through it and go step by step. There are many different kinds of models that you can build using transformers. Some models take in audio and produce a transcript. This sentence comes from a model going the other way around, producing synthetic speech just from text. All those tools that took the world by storm in 2022, like Dolly and Midjourney, that take in a text description and produce an image, are based on transformers. Even if I can't quite get it to understand what a pie creature is supposed to be, I'm still blown away that this kind of thing is even remotely possible. And the original transformer, introduced in 2017 by Google, was invented for the specific use case of translating text from one language into another. But the variant that you and I will focus on, which is the type that underlies tools like ChatGPT, will be a model that's trained to take in a piece of text, maybe even with some surrounding images or sound accompanying it, and produce a prediction for what comes next in the passage. That prediction takes the form of a probability distribution over many different chunks of text that might follow. At first glance, you might think that predicting the next word feels like a very different goal from generating new text. But once you have a prediction model like this, a simple thing you could try to make it generate a longer piece of text is to give it an initial snippet to work with, have it take a random sample from the distribution it just generated, append that sample to the text, and then run the whole process again to make a new prediction based on all the new text, including what it just added. I don't know about you, but it really doesn't feel like this should actually work. In this animation, for example, I'm running GPT-2 on my laptop and having it repeatedly predict and sample the next chunk of text to generate a story based on the seed text. And the story just doesn't actually really make that much sense. But if I swap it out for API calls to GPT-3 instead, which is the same basic model, just much bigger, suddenly, almost magically, we do get a sensible story, one that even seems to infer that a pie creature would live in a land of math and computation. This process here of repeated prediction and sampling is essentially what's happening when you interact with ChatGPT or any of these other large language models, and you see them producing one word at a time. In fact, one feature that I would very much enjoy is the ability to see the underlying distribution for each new word that it chooses. Let's kick things off with a very high-level preview of how data flows through a transformer. We will spend much more time motivating and interpreting and expanding on the details of each step, but in broad strokes, when one of these chatbots generates a given word, here's what's going on under the hood. First, the input is broken up into a bunch of little pieces. These pieces are called tokens, and in the case of text, these tend to be words or little pieces of words or other common character combinations. If images or sound are involved, then tokens could be little patches of that image or little chunks of that sound. Each one of these tokens is then associated with a vector, meaning some list of numbers, which is meant to somehow encode the meaning of that piece. If you think of these vectors as giving coordinates in some very high-dimensional space, words with similar meanings tend to land on vectors that are close to each other in that space. This sequence of vectors then passes through an operation that's known as an attention block, and this allows the vectors to talk to each other and pass information back and forth to update their values. For example, the meaning of the word model in the phrase a machine learning model is different from its meaning in the phrase a fashion model. The attention block is what's responsible for figuring out which words in the context are relevant to updating the meanings of which other words, and how exactly those meanings should be updated. And again, whenever I use the word meaning, this is somehow entirely encoded in the entries of those vectors. After that, these vectors pass through a different kind of operation, and depending on the source that you're reading, this will be referred to as a multi-layer perceptron or maybe a feed-forward layer. And here, the vectors don't talk to each other. They all go through the same operation in parallel. And while this block is a little bit harder to interpret, later on we'll talk about how this step is a little bit like asking a long list of questions about each vector, and then updating them based on the answers to those questions. All of the operations in both of these blocks look like a giant pile of matrix multiplications, and our primary job is going to be to understand how to read the underlying matrices. I'm glossing over some details about some normalization steps that happen in between, but this is, after all, a high-level preview. After that, the process essentially repeats. You go back and forth between attention blocks and multi-layer perceptron blocks, until at the very end, the hope is that all of the essential meaning of the passage has somehow been baked into the very last vector in the sequence. We then perform a certain operation on that last vector that produces a probability distribution over all possible tokens, all possible little chunks of text that might come next. And like I said, once you have a tool that predicts what comes next given a snippet of text, you can feed it a little bit of seed text and have it repeatedly play this game of predicting what comes next, sampling from the distribution, appending it, and then repeating over and over. Some of you in the know may remember how, long before ChatGPT came into the scene, this is what early demos of GPT-3 looked like. You would have it autocomplete stories and essays based on an initial snippet. To make a tool like this into a chatbot, the easiest starting point is to have a little bit of text that establishes the setting of a user interacting with a helpful AI assistant, what you would call the system prompt. And then you would use the user's initial question or prompt as the first bit of dialogue. And then you have it start predicting what such a helpful AI assistant would say in response. There is more to say about an added step of training that's required to make this work well, but at a high level, this is the general idea. In this chapter, you and I are going to expand on the details of what happens at the very beginning of the network, at the very end of the network, and I also want to spend a lot of time reviewing some important bits of background knowledge, things that would have been second nature to any machine learning engineer by the time transformers came around. If you're comfortable with that background knowledge and a little impatient, you could probably feel free to skip to the next chapter, which is going to focus on the attention blocks, generally considered the heart of the transformer. After that, I want to talk more about these multi-layer perceptron blocks, how training works, and a number of other details that will have been skipped up to that point. For broader context, these videos are additions to a mini-series about deep learning. And it's okay if you haven't watched the previous ones, I think you can do it out of order. But before diving into transformers specifically, I do think it's worth making sure that we're on the same page about the basic premise and structure of deep learning. At the risk of stating the obvious, this is one approach to machine learning, which describes any model where you're using data to somehow determine how a model behaves. What I mean by that is, let's say you want a function that takes in an image and it produces a label describing it, or our example of predicting the next word given a passage of text, or any other task that seems to require some element of intuition and pattern recognition. We almost take this for granted these days, but the idea with machine learning is that rather than trying to explicitly define a procedure for how to do that task in code, which is what people would have done in the earliest days of AI, instead, you set up a very flexible structure with tunable parameters, like a bunch of knobs and dials, and then, somehow, you use many examples of what the output should look like for a given input to tweak and tune the values of those parameters to mimic this behavior. For example, maybe the simplest form of machine learning is linear regression, where your inputs and your outputs are each single numbers, something like the square footage of a house and its price. And what you want is to find a line of best fit through this data, to predict future house prices. That line is described by two continuous parameters, say the slope and the y-intercept, and the goal of linear regression is to determine those parameters to closely match the data. Needless to say, deep learning models get much more complicated. GPT-3, for example, has not 2, but 175 billion parameters. But here's the thing, it's not a given that you can create some giant model with a huge number of parameters without it either grossly overfitting the training data or being completely intractable to train. Deep learning describes a class of models that in the last couple decades have proven to scale remarkably well, What unifies them is that they all use the same training algorithm. It's called backpropagation. We talked about it in previous chapters. And the context that I want you to have as we go in is that in order for this training algorithm to work well at scale, these models have to follow a certain specific format. And if you know this format going in, it helps to explain many of the choices for how a transformer processes language, which otherwise run the risk of feeling kind of arbitrary. First, whatever kind of model you're making, the input has to be formatted as an array of real numbers. This could simply mean a list of numbers. It could be a two-dimensional array, or very often you deal with higher dimensional arrays, where the general term used is tensor. You often think of that input data as being progressively transformed into many distinct layers, where again, each layer is always structured as some kind of array of real numbers, until you get to a final layer which you consider the output. For example, the final layer in our text processing model is a list of numbers representing the probability distribution for all possible next tokens. In deep learning, these model parameters are almost always referred to as weights. And this is because a key feature of these models is that the only way these parameters interact with the data being processed is through weighted sums. You also sprinkle some nonlinear functions throughout, but they won't depend on parameters. Typically, though, instead of seeing the weighted sums all naked and written out explicitly like this, you'll instead find them packaged together as various components in a matrix vector product. It amounts to saying the same thing. If you think back to how matrix vector multiplication works, each component in the output looks like a weighted sum. It's just often conceptually cleaner for you and me to think about matrices that are filled with tunable parameters that transform vectors that are drawn from the data being processed. For example, those 175 billion weights in GPT-3 are organized into just under 28,000 distinct matrices. Those matrices in turn fall into 8 different categories, and what you and I are going to do is step through each one of those categories to understand what that type does. As we go through, I think it's kind of fun to reference the specific numbers from GPT-3 to count up exactly where those 175 billion come from. Even if nowadays there are bigger and better models, this one has a certain charm as the first large language model to really capture the world's attention outside of ML communities. Also, practically speaking, companies tend to keep much tighter lips around the specific numbers for more modern networks. I just want to set the scene going in, that as you peek under the hood to see what happens inside a tool like ChatGPT, almost all of the actual computation looks like matrix vector multiplication. There's a little bit of a risk getting lost in the sea of billions of numbers, but you should draw a very sharp distinction in your mind between the weights of the model, which I'll always color in blue or red, and the data being processed, which I'll always color in gray. The weights are the actual brains. They are the things learned during training, and they determine how it behaves. The data being processed simply encodes whatever specific input is fed into the model for a given run, like an example snippet of text. With all of that as foundation, let's dig into the first step of this text processing example, which is to break up the input into little chunks and turn those chunks into vectors. I mentioned how those chunks are called tokens, which might be pieces of words or punctuation. But every now and then in this chapter, and especially in the next one, I'd like to just pretend that it's broken more cleanly into words. Because we humans think in words, this will just make it much easier to reference little examples and clarify each step. The model has a predefined vocabulary, some list of all possible words, say 50,000 of them. And the first matrix that we'll encounter, known as the embedding matrix, has a single column for each one of these words. These columns are what determines what vector each word turns into in that first step. We label it WE, and like all the matrices we see, its values begin random, but they're going to be learned based on data. Turning words into vectors was common practice in machine learning long before transformers, but it's a little weird if you've never seen it before, and it sets the foundation for everything that follows, so let's take a moment to get familiar with it. We often call this embedding a word, which invites you to think of these vectors very geometrically, as points in some high-dimensional space. Visualizing a list of 3 numbers as coordinates for points in 3D space would be no problem, but word embeddings tend to be much, much higher dimensional. In GPT-3, they have 12,288 dimensions, and as you'll see, it matters to work in a space that has a lot of distinct directions. In the same way that you could take a 2-dimensional slice through a 3D space and project all the points onto that slice, For the sake of animating word embeddings that a simple model is giving me, I'm going to do an analogous thing by choosing a three-dimensional slice through this very high-dimensional space and projecting the word vectors down onto that and displaying the results. The big idea here is that as a model tweaks and tunes its weights to determine how exactly words get embedded as vectors during training, it tends to settle on a set of embeddings where directions in the space have a kind of semantic meaning. For the simple word-to-vector model I'm running here, if I run a search for all the words whose embeddings are closest to that of tower, you'll notice how they all seem to give very similar tower-ish vibes. And if you want to pull up some Python and play along at home, this is the specific model that I'm using to make the animations. It's not a transformer, but it's enough to illustrate the idea that directions in the space can carry semantic meaning. A very classic example of this is how if you take the difference between the vectors for woman and man, something you would visualize as a little vector in the space connecting the tip of one to the tip of the other, it's very similar to the difference between king and queen. So let's say you didn't know the word for a female monarch. You could find it by taking king, adding this woman minus man direction, and searching for the embeddings closest to that point. At least, kind of. Despite this being a classic example for the model I'm playing with, the true embedding of queen is actually a little farther off than this would suggest, presumably because the way that queen is used in training data is not merely a feminine version of king. When I played around, family relations seem to illustrate the idea much better. The point is, it looks like during training, the model found it advantageous to choose embeddings such that one direction in this space encodes gender information. Another example is that if you take the embedding of Italy and you subtract the embedding of Germany, and then you add that to the embedding of Hitler, you get something very close to the embedding of Mussolini. It's as if the model learned to associate some directions with Italianness and others with World War II Axis leaders. Maybe my favorite example in this vein is how in some models, if you take the difference between Germany and Japan and you add it to sushi, you end up very close to bratwurst. Also, in playing this game of finding nearest neighbors, I was very pleased to see how close cat was to both beast and monster. One bit of mathematical intuition that's helpful to have in mind, especially for the next chapter, is how the dot product of two vectors can be thought of as a way to measure how well they align. Computationally, dot products involve multiplying all the corresponding components and then adding the results, which is good since so much of our computation has to look like weighted sums. Geometrically, the dot product is positive when vectors point in similar directions. It's 0 if they're perpendicular, and it's negative whenever they point in opposite directions. For example, let's say you were playing with this model and you hypothesize that the embedding of cats minus cat might represent a sort of plurality direction in this space. To test this, I'm going to take this vector and compute its dot product against the embeddings of certain singular nouns and compare it to the dot products with the corresponding plural nouns. If you play around with this, you'll notice that the plural ones do indeed seem to consistently give higher values than the singular ones, indicating that they align more with this direction. It's also fun how if you take this dot product with the embeddings of the words 1, 2, 3, and so on, they give increasing values, so it's as if we can quantitatively measure how plural the model finds a given word. Again, the specifics for how words get embedded is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pile of weights in our model. And using the GPT-3 numbers, the vocabulary size specifically is 50,257. And again, technically this consists not of words per se, but of tokens. And the embedding dimension is 12,288. Multiplying those tells us this consists of about 617 million weights. Let's go ahead and add this to a running tally, remembering that by the end, we should count up to 175 billion. In the case of transformers, you really want to think of the vectors in this embedding space as not merely representing individual words. For one thing, they also encode information about the position of that word, which we'll talk about later. But more importantly, you should think of them as having the capacity to soak in context. A vector that started its life as the embedding of the word king, for example, might progressively get tugged and pulled by various blocks in this network, so that by the end it points in a much more specific and nuanced direction that somehow encodes that it was a king who lived in Scotland, and who had achieved his post after murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by the surroundings, and sometimes this includes context from a long distance away. So in putting together a model that has the ability to predict what word comes next, the goal is to somehow empower it to incorporate context efficiently. To be clear, in that very first step, when you create the array of vectors based on the input text, each one of those is simply plucked out of the embedding matrix. So initially, each one can only encode the meaning of a single word without any input from its surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words could represent. The network can only process a fixed number of vectors at a time, known as its context size. For GPT-3, it was trained with a context size of 2048, so the data flowing through the network always looks like this array of 2048 columns, each of which has 12,000 dimensions. This context size limits how much text the transformer can incorporate when it's making a prediction of the next word. This is why long conversations with certain chatbots, like the early versions of ChatGPT, often gave the feeling of the bot kind of losing the thread of conversation as you continued too long. We'll go into the details of attention in due time, but skipping ahead, I want to talk for a minute about what happens at the very end. Remember, the desired output is a probability distribution over all tokens that might come next. For example, if the very last word is professor, and the context includes words like Harry Potter, and immediately preceding, we see least favorite teacher, and also if you give me some leeway by letting me pretend the tokens simply look like full words, then a well-trained network that had built up knowledge of Harry Potter would presumably assign a high number to the word Snape. This involves two different steps. The first one is to use another matrix that maps the very last vector in that context to a list of 50,000 values, one for each token in the vocabulary. Then there's a function that normalizes this into a probability distribution. It's called softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction, when after all, in that last step, there are thousands of other vectors in the layer just sitting there with their own context-rich meanings. This has to do with the fact that in the training process, it turns out to be much more efficient if you use each one of those vectors in the final layer to simultaneously make a prediction for what would come immediately after it. There's a lot more to be said about training later on, but I just want to call that out right now. This matrix is called the unembedding matrix, and we give it the label WU. Again, like all the weight matrices we see, its entries begin at random, but they are learned during the training process. Keeping score on our total parameter count, this unembedding matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding dimension. It's very similar to the embedding matrix, just with the order swapped, so it adds another 617 million parameters to the network, meaning our count so far is a little over a billion. A small, but not wholly insignificant fraction of the 175 billion that we'll end up with in total. As the very last mini lesson for this chapter, I want to talk more about the softmax function, since it makes another appearance for us once we dive into the attention blocks. The idea is that if you want a sequence of numbers to act as a probability distribution, say a distribution over all possible next words, then each value has to be between 0 and 1, and you also need all of them to add up to 1. However, if you're playing the deep learning game, where everything you do looks like matrix vector multiplication, the outputs that you get by default don't abide by this at all. The values are often negative or much bigger than 1, and they almost certainly don't add up to 1. Softmax is the standard way to turn an arbitrary list of numbers into a valid distribution in such a way that the largest values end up closest to 1, and the smaller values end up very close to 0. That's all you really need to know. But if you're curious, the way that it works is to first raise e to the power of each of the numbers, which means you now have a list of positive values, and then you can take the sum of all those positive values and divide each term by that sum, which normalizes it into a list that adds up to 1. You'll notice that if one of the numbers in the input is meaningfully bigger than the rest, then in the output, the corresponding term dominates the distribution. So if you were sampling from it, you'd almost certainly just be picking the maximizing input. But it's softer than just picking the max in the sense that when other values are similarly large, they also get meaningful weight in the distribution, and everything changes continuously as you continuously vary the inputs. In some situations, like when ChatGPT is using this distribution to create a next word, there's room for a little bit of extra fun by adding a little extra spice into this function with a constant t thrown into the denominator of those exponents. We call it the temperature since it vaguely resembles the role of temperature in certain thermodynamics equations. And the effect is that when t is larger, you give more weight to the lower values, meaning the distribution is a little bit more uniform. And if t is smaller, then the bigger values will dominate more aggressively. Where in the extreme, setting t equal to 0 means all of the weight goes to that maximum value. For example, I'll have GPT-3 generate a story with the seed text, "Once upon a time there was A," but I'm going to use different temperatures in each case. Temperature 0 means that it always goes with the most predictable word. And what you get ends up being kind of a trite derivative of Goldilocks. A higher temperature gives it a chance to choose less likely words, but it comes with a risk. In this case, the story starts out a bit more originally, about a young web artist from South Korea, but it quickly degenerates into nonsense. Technically speaking, the API doesn't actually let you pick a temperature bigger than 2. There is no mathematical reason for this. It's just an arbitrary constraint imposed, I suppose, to keep their tool from being seen generating things that are too nonsensical. So if you're curious, the way this animation is actually working is I'm taking the 20 most probable next tokens that GPT-3 generates, which seems to be the maximum they'll give me, and then I tweak the probabilities based on an exponent of 1/5. As another bit of jargon, in the same way that you might call the components of the output of this function probabilities, people often refer to the inputs as logits, or some people say logits, some people say logits. I'm going to say logits. So for instance, when you feed in some text, you have all these word embeddings flow through the network, and you do this final multiplication with the unembedding matrix. Machine learning people would refer to the components in that raw, unnormalized output as the logits for the next word prediction. A lot of the goal with this chapter was to lay the foundations for understanding the attention mechanism, Karate Kid wax on, wax off style. You see, if you have a strong intuition for word embeddings, for softmax, for how dot products measure similarity, and also the underlying premise that most of the calculations have to look like matrix multiplication with matrices full of tunable parameters, then understanding the attention mechanism, this cornerstone piece in the whole modern boom in AI, should be relatively smooth. For that, come join me in the next chapter. As I'm publishing this, a draft of that next chapter is available for review by Patreon supporters. A final version should be up in public in a week or two. It usually depends on how much I end up changing based on that review. In the meantime, if you want to dive into attention, and if you want to help the channel out a little bit, it's there waiting.
So what do you think? Quite impressive, right? Any comments? There was a lot of information in this video. This is why I recommend you to watch it calmly yourself. Maybe a bit slower also. Velocity was just 1, but it was quite quick. But you see many of the ideas we have mentioned. In particular, you see very clearly this dynamical system perspective. Then you also see that you have to make the model quite complex, high dimensional, so that out of all the information you are putting on it, the model is able to figure out what the relevant directions and dimensions are. The model has to learn about gender, about colors, about sizes. So there is plenty of, and you see also what I mentioned the other day, when you are reading books, it's not clear what the label is. Even when you are translating text, the one-to-one translation of every word doesn't really work, because different languages use different grammars and different structures. So in some languages there are declinations. So expressions that in some languages need 2 words in one language can be compressed into one single word by declination. So it's not even clear that there is a one-to-one correspondence between words. So this paradigm of supervised learning, in which you give features on one side and on the other hand a label to each of them, is not so easy to implement in this context. And as explained in the video, the solution the computer scientists found for this is to, out of a given text, generate labels by the exercise of learning the next word. And as it was said in the video as well, creating text, generating text is not that different from guessing the next word. And actually, when you think how we mathematicians work and do research, is very much that way. We learn many books, we take many classes, we listen to many talks, we read many papers, and in this way we learn how arguments are concatenating ideas. And then eventually, out of this, we learn some, systematic methodologies. Like, for instance, if you have to compute a definite integral, well, clearly, this is the fundamental theorem of calculus. First, you compute the primitive, and then you evaluate the primitive f, capital F at b minus capital F at a. So there is a clear structure on this, in this method, in this proof. But when you are doing research, the text is not written. You don't know what the result you are looking for is. And therefore, you don't even know what the proof has to be. But somehow we are operating by guessing the next step. So I have what I have. I have to do something next. Then out of all the information I have on my brain and all the connections I have realized during so many years of training, I have an intuition of what the next step can be. And then I try. And I see that the next step either fails or opens a new gate. If it opens a new gate, I continue the argument. If it doesn't lead to anything, I have to go back, because I'm walking like in a labyrinth. But this is what happens also in machine learning. Even ChatGPT, as we said, is fantastic, but sometimes gives you the wrong answer, or gives you simply an answer that is not even wrong or true, is simply fake, is new, is virtual, doesn't actually correspond to any existing reality, like, for instance, in bibliographical references. Okay, so there is a lot of this explained in this video. I have found one solution in the numerical sense for Cahn-Hilliard equation 6th order. Then I can use deep learning or neural network to make fitting parameters. Yes, of course. So the data, the models, the discussions we had about control or fitting dynamic data. So you can think control as fitting static. We use control in a dynamic manner, but just to fit data from t equals 0 to t equal capital T, or given x, fx equal y, fx equal L, the label. So you are fitting data. So whenever you have data, you can use neural networks to interpolate this data. So as you say, this is actually a very good exercise for numerical analysts to test the accuracy of these methodologies. You can do the following. You take Cahn-Hilliard equation, order 6. Doesn't really matter which equation you are considering. It can be, I don't know, the wave equation, the Klein-Gordon equation, the KdV equation, the Heat equation, the Burgers equation, doesn't really matter. And then you take a grid. You are in the interval of, for instance, 0, 1. You take a grid, you have 10 points. You do numerical simulation of this PDE from t equals 0 to t equal capital T. And you have the MATLAB program, you can do the numerical simulation. And then you can do the numerical simulation is therefore at t equal capital T, at t equal 1, it leads you to a vector of 10 components, the numerical solution at the final time, just 10 points, a vector of 10 components. So then you take many initial data. I don't know, you take, for instance, a Fourier perspective. You take sinus kx from k equal 0 to 25, or k equal 1 to 25. You take 25 different initial data. You solve with the MATLAB solver, you solve this numerically, this PD 25 times. And therefore, you are building what? You have the value of a function that is mapping r to the power 10 into r to the power 10, and you have this function defined on 25 different points. Then you can build a neural network, and you can guarantee that this neural network, for every initial datum, is mimicking what the numerical code does and gives you the corresponding final solution. So you have built through the neural network, you have built a black box that is able to do on these 25 different instances, different initial data, the same as the solution of the PD does a long time. Okay, the PD is doing vertically, X and T, and we are doing here horizontally along a deep neural network from initial to final. So you have a black box full of neurons and full of activations and coefficients that is able to reproduce this. You can do that. Of course, the question is how good this black box is going to be when you ask the numerical code the neural network black box to guess a new solution that the black box didn't see before. So now, if I have trained the neural network to do the solution of the PDE for sinusoidal kx for k from 1 to 25, will the black box be able to compute the solution for, say, sinus kx with k equal 40? This is highly unclear. But actually, this issue is also very delicate in the classical numerical analysis. So recall that concerning these fake answers that ChatGPT gives. So these fake answers, you can get them also in the context of PDEs and numerical analysis of PDEs. So recall what the definition of convergent numerical algorithm is for an ODE or for a PDE. We say, for a PDE, we say that a numerical algorithm converges when for every PDE solution, you can get a sequence approximating numerical solutions that converges to this PDE solution. Okay, so this is what numerical analysis says. But it doesn't say that the numerical algorithm is not building many other numerical solutions that will not actually converge to the physical solution. And this is typically what happens with wave propagation and high frequency solutions. That is, when you fix the mesh size delta x, you can only expect to capture low frequency components of the system. If you will rely on the numerical algorithm to capture the high frequency solutions of the true problem through the numerics, you will see plenty of numerical artifacts, very much like these fake bibliographical references that the ChatGPT is generating. So the difference between numerical analysis and say machine learning, is that in numerical analysis we have a much broader body of literature that tries to explain this, even though the theory is not completely generic. For instance, for Hamiltonian systems, one of the classical topics in numerics of Hamiltonian systems is to determine whether the numerical solver you are using, for instance, Runge-Kutta solvers, whether the numerical solver is able to reproduce the periodicity pattern of the Hamiltonian system. For instance, when you are doing numerical simulations of the solar systems, for me, it's not sufficient that you tell me that the numerical algorithm is convergent. I would like to know whether the numerical algorithm is able to guess that, the system in Earth is evolving with a 24 hours period, or whether, the system is able to capture the seasons every 3 months. Okay? So you need periodicity on the solution of your system. Convergence is not sufficient. If you take for these Hamiltonian periodic systems, if you take an Euler implicit scheme that is too dissipative, what the Euler dissipative scheme does is takes all the planets that are rotating and all of them will collapse to zero, to the sun. So the numerical algorithm will anticipate exponential convergence collapse of the solar system. If you take, by the contrary, an Euler explicit scheme in which you don't have the good, say, CFL condition, you can have trajectories that are expanding and that exponentially diverge. So I don't want, when I am simulating the solar system, that the numerics either anticipates that all planets diverge to infinity or all of them collapse to the sun. I really want that the periodicity is captured. And this is what is called symplectic numerical algorithms. And you can see the books of Ernst Heider on this, for instance. This is a beautiful theory. But you see, the theory is for Hamiltonian systems, for Runge-Kutta solvers, and then within the class of Runge-Kutta solvers, you can say which ones are the ones that are able to capture the qualitative dynamics of the dynamical system. And then in MATLAB, typically, when you use the Runge-Kutta solvers, MATLAB will preferably choose automatically those that are, symplectic or geometric, so that in case your ODE has some periodicity or a specific time-like pattern, the numerics exhibits this. So the question is, this was done for PDEs also. For instance, we know that this was the PhD thesis in our team by Liviu Ignat, now in professor in Bucharest. For instance, if you ask what are the numerical schemes that are able to preserve the street-chart dispersive estimates for Schrödinger equations, well, we know that there are some schemes that do preserve the dispersive properties and some others that don't. If you go back earlier in the literature, you could even think on simpler problems. So the Laplace equation, we know the Dirichlet Laplacian has the maximum principle. If you apply a non-negative force, the solution is positive, it's non-negative. And then you ask, do all finite element methods satisfy this property that for an applied positive force, the response, the solution of the discrete system is positive? Well, not. You need some restrictions on the measures. Why? Because you need the rigidity matrix of the system to be diagonal dominant. I think it's called N matrix. So that positive, and then the diagonal term dominates the sum of the absolute value of all other terms on a line of the matrix. And I think this was part of the early work of probably Ciarlet and Rabiar in the 70s. So there is a lot of work done in the PDE theory in order to simply guarantee that the numerical algorithm does something like generalization well. So for instance, the only thing we are asking to the finite element method there is to check whether the finite element method has learned the maximum principle. F positive, U positive. This is very elementary. This is not very ambitious, right? Yet you need to fine-tune your finite element method, and you get to the conclusion that in order to have this property, you need the triangles of your finite element mesh to be more or less not too far from equilateral triangles. If there is too much eccentricity on the triangles, this property is lost. So you see the giant gap between the kind of, despite of decades of numerical analysis, right? So by the 60s, the foundations of numerical analysis, many of them were already established. So in the book of Isaacson-Keller in 68, I think, all the foundational methods in numerical analysis are described. So 60 years later, we have a good understanding of specific properties for specific problems. Another good example is numerics for conservation laws. How do you have to build a numerical algorithm in order to see that for a Barger's equation there is a shock-like solution? Or numerics for free boundary problems. How can you develop the numerical algorithm so that whenever there is a free boundary in your evolution in mechanics, this free boundary is well captured? So we have spent 60 years doing things like this in particular cases. And now suddenly we invent this monster, and we want to understand whether, this monster knows about colors, about sizes, about gender, about locations, about history, about mathematics, about painting. We are asking all kinds of things, and we expect a reliable answer. So mathematically, this is extremely sophisticated, and the challenge is giant. So this is why it's such a good topic for mathematicians to work on. Okay, so I think I said this. So there are many different ways. So there is not a unique way in which you can employ these neural network models. But as I said before, it can be, for instance, the measurements I have taken on the temperature in the different offices in my building. I have a thermostat in every office. There are 100 offices in my Felix Klein building. And then, this is put on a vector, right, of 100 components. In this case, the state represents the temperature in each of these 100 offices. But if I am dealing with image processing, and as we did the first day, image pattern recognition, more generally speaking, pattern recognition, recognize pattern. And then pattern can mean many things. It can be also crime or cybercrime. This is, of course, very important in cybersecurity. So this has happened to all of us, right? So at a given time, you get a call or a message from your bank saying, are you using your card in order to buy something online for, say, 2.49 euros? And say, no, I'm not using my card. I am actually, driving. Well, someone is trying to use your card. I mean, they are trying to, they got part of the information that your card needs, and this is a fake operation. So pattern recognition can be also about, health, can be about crime, just pattern on any kind of human activity or natural phenomena. So then in each of these applications, the vector means something else. So in the case of digits to be classified according to, the one they represent from 0 to 9, every digit was made a picture. A picture was 28 times 28. A vector is 784 components. And in that case, every entry on every component of this vector meant how much drawing there is on this specific pixel. It can be either empty, or it can be full, 0, 1, or it can be, gray, then 0.6, and so on. So in each application, the vector represents something else. So these ideas are very powerful and can be used in all applications, basically, because the fundamental principle, as I have tried to show you, is that control theoretical tools allow you to explain why these synthetic models have expressivity power. They can represent data, and they can do it even in a dynamical manner. Of course, the key is generalization, and then generalization is, as I was trying to explain you when referring to PDEs, a very complex problem. And depends on the architecture, depends on the training, depends on the size of the model, depends on the application you have in mind. And well, so of course, this is the challenge. So we use these methods for some things, but not for everything. So when we see a neural network that is performing well 93% of the time, we say, oh, this is fantastic. You see, it's doing it right 93% of the time. Yes, but you will not purchase an airplane ticket in a company for which 7% of the airplanes will crash, statistically, right? So 93% is a lot, depending on what is the application. In normal life, for us, guarantee is much more than 93%. It's 99.99999. And this is very hard to achieve. I hope you enjoyed, and I hope you got at least interested on the topic and tempted to work on it. Don't hesitate to send me an email anytime with further questions. I will be pleased to talk to you in person or communicate with you.